Welcome, gentlemen.
Everybody would prefer quality to quantity, so I'm sure the people that have come here are interested in listening to some conversation about earthquakes. I've had some on this thunderstorm. The next slide talks about some of these earthquakes. And it's interesting that in science in general, and in earthquakes maybe more than most, and the only thing we know about everything I'm going to tell you is that it's all wrong. Okay? This is work in progress. We haven't arrived anywhere yet, and science progresses not by showing that things are right, but by putting up ideas which will subsequently be shown to be wrong, and that moves us forward. So this is the scientific method. It's the reason why anybody should aspire to work in science, because there are no sacred cows, and scientists enjoy. What makes your name as a scientist is in showing that things that people thought were right before are actually wrong. And in doing that, you move things forward. So young scientists among you, really, that's fundamentally important. Newton was very clever. He worked out the basis of the classical view of gravity. And a lot of what I'm going to talk about here requires that Newton's laws are used throughout a lot of what I'm talking about. But I'm going to show you a lot of information that comes from GPS satellite technology. And if you use Newton's equations to try and work out where the satellites are, you get the answer wrong by a sufficient amount that the position that you locate where you are is completely wrong. So if you use Newton, your sat-nav doesn't work in your car. You have to use Einstein, because Einstein corrected that view of gravity. So in most applications we still use Newton, but the correction, the way in which Einstein understands gravity is completely different, and showed that in some fundamental way Newton was wrong. It's a terrible thing for science to say that. And in the future, there's no doubt that we will find that there are situations in which Einstein's view of gravity isn't sufficient to explain the data either, and then we move on to something else. So all of this is provisional, all of it's moving forward. I think over the last 10 years we're in a really fantastic growth in terms of our understanding of earthquakes, and I'm going to try and give you a snapshot of some of the work we're doing. It's a team sport, so there are people from all over the world on the list here that we work with. And amazingly, for me, who was never interested in social science or anything like that, that was soft stuff, I'm working increasingly with a lot of social scientists to try and see if we can use the science that we're starting to learn. There's still a big debate among scientists whether or not we know enough to start meddling in social science and get people to listen to us. I'm one of those who strongly feel that we do, and I'll try and persuade you of that as well. And then at the end of the lecture, I'm going to show you something completely new. There are two things that are published in this lecture. The last stuff is really exciting. It's about trying to learn what we can maybe do in poor countries to increase the resilience of communities based on the type of science we're doing here. So I'm going to start off a general introduction to how things work, and then show you how we're trying to understand the physics of the earthquake process. I'm going to make some forecasts about what's going to happen next in Sumatra, and then I'm going to try and explain to you how we're working with people there in the government and non-government organizations and other groups to try and make people more resilient to earthquakes we think are going to happen in the near future. And then I'm going to talk to you about the interface between physics and social science in a way in which we might be able to identify specific things that poor countries can do to make them more resilient. Okay, so that's a sort of prospectus. We've heard of some of these already. I was given a lecture, something like this, about a year ago, and I went onto the USGS website. All these figures are pretty much wrong, but they give you more or less the right idea. And the Tangshan earthquake in China, we reckon that the divergence of the number of deaths from something like 200,000 to something like 600,000 is nothing to do with counting deaths. It's just to do with the politics of the Chinese government wanted to downplay the number. So Western scientists believe that it was probably in the order of 500,000 or more, and the Chinese government told us that it was about 200,000, so I think that's the main cause of that. The disturbing thing, this is the 5 worst killer earthquakes in 2 million years of the human species. Let's say we're about 1 million or 2 million years old. These are the worst. We know that prior to the Middle Ages, the population of the world was so small that it's very, very unlikely that any earthquake prior to 1500 would have killed more people than this. So we believe these are the worst 5. The horrible thing about this is that 2 of the worst 5 happened in the last 10 or 12 years. So, and 3 of them have happened within our lifetime, within my lifetime anyway, so these are a bit Earthquakes are becoming more lethal, despite the fact that the physics of the planet isn't changing at all, but the demography of the human species is changing, and more poor people, dominantly poor people, are being forced to live in more and more marginal positions, and the exponential increase in the number of people dying in earthquakes is set to increase, or to continue with that trend for the foreseeable future, unless we are able to intervene in either in society or in better understanding of the science, and ideally a combination of the 2, so that we can try and stop that exponential increase in the number of deaths. And that's really the big scale motivation for what we're doing. All of you know something about plate tectonics. Basically, the convection in the Earth's mantle, which is driven by radioactivity, is moving plates around at the surface, and where they interact, new crust is being created in the middle of the ocean ridges as convection moves towards the surface. And what I'm going to spend most of this lecture talking about is here, where the Indian Ocean plate is being forced under the Sumatran plate. Incidentally, the junctions between these plates are where all the earthquakes happen. But this is Sumatra, so we have the Indian plate being forced under Sumatra here, which is a part of the Eurasian plate actually. Here's a classic cross-section taken from a general geophysics textbook, in which you can see all the main features. You've got the oceanic plate being pushed down under. You've got a trench here, which is well shown in the bathymetry here. You have an outer arc high. Really important, this row of islands. It allows us, I'll talk about this in more in a minute, but it allows us to put our instruments right on top of where the earthquakes are happening. Then you have another fault here, which I'm not going to talk much about, and a row of volcanoes, a volcanic arc here. So Sumatra is a classic textbook type example of subduction zone. It's got all the features, and most importantly for here, this area where the ocean plate is being pushed under the continental plate, it doesn't happen smoothly. It sticks and then it slips. And those slippage events are the big earthquakes. I'm going to show you the technology that allows us to say really accurately how fast these plates are moving in different places. And that allows us to really understand how strain is building up within the crust. And I'm going to talk particularly about the city of Padang. I had a video, which isn't going to work, but it might work actually on this one. So I'm going to talk about Padang. Please work. Yeah, okay. So Padang's here. We're going to fly into it now, because I wanted to look at the vulnerability of the people living in this city. So this is the city here. About 850,000 people live here. You can see how low-lying it is. The whole downtown area is less than 10 meters above sea level, and that's really important. So you've got about 600,000-700,000 people living at a height of less than 10 meters above sea level, and as I'm going to try and persuade you that they're all living in the threat of a major earthquake which will generate a tsunami, and I'll try and help you to understand what we know about that, and probably more importantly what we don't know about it, and we're trying to understand. Okay, what's the technology? 2 types of instruments really give us a completely new way of looking at earthquakes. The first is a seismometer. This is one of the British Geological Survey school seismometer equipment. get it on your geography teachers, get them to buy a school seismometer. It's a fantastic piece of instrumentation, which allows you to take part in international experiments in seismology. That mass basically stays in the one place as the ground shakes, and there's a bit of electronics that's able to measure the relative movement between the ground and that mass. This is the inside of a modern broadband seismometer that we deploy in the field. And these basically can record over very, very wide ranges of frequency the tiniest vibrations of the ground. So broadband seismometry has really come of age over the last 10 or 20 years. It's a major source of information for what I'm going to talk about. We have some technical problems here. I hope they won't happen again. That's a clever device. Really fantastic. Okay, that might switch off again a couple of times. I don't have a lead for it, and the computer here wouldn't run this presentation, so I've turned the power usage down to minimum. Okay, the next thing is there are a constellation of satellites permanently in orbit around the planet, which are designed to allow geographical positioning systems to work. So the sat-nav in your car works because of these. And as I said, we need to use Einstein rather than Newton to work out the position of these accurately enough. But when we do this properly, and these are military technologies originally which have been released for scientific use, we're able to measure the position of a point on the surface of the Earth, accurate to about 1 millimeter, and we can watch how that changes over time, and basically watch the Earth deforming under the forces that are generated within it. This is not good. Okay. Okay, so what do we see with these satellites, with these GPS instruments? What we see is that over a period of several hundred years, the plates moving together slowly deform the Earth's crust, and islands offshore are pushed onto the water for a period of about 200 years, and then the frictional forces between these two plates here become insufficient to hold the forces, and the result is that somewhere under the surface an earthquake nucleates, somewhere breaks, maybe only the size of your thumbnail breaks, and it generates a stress concentration around the outside, and that spreads outwards and generates a big earthquake. All big earthquakes start as very small earthquakes, and one of the problems with predicting earthquakes or understanding whether an earthquake is going to be big or not is we don't fully understand the physics of how that process happens. This is a big issue for us. But we know for sure that sometime a big earthquake happens over a period of a few minutes. The strain energy that's been collected for 200 years is released, and the result is, as the island pops up, it pushes a column of water above it, and the resulting column of water, of course, is unstable. It collapses, and generally for Sumatra, it hits the shore about 30 minutes after the earthquake. I can explain more about that later. So, 2004, at about 8:30 in the morning, on Boxing Day in 2004, that thumbnail size broke somewhere just north of the island of Simeulue, and over the next 10 minutes or so, the junction between the two plates ruptured, and this is a simulation of what the seafloor surface did. So you can see that along out near the oceanic trench, the seafloor moved upwards vertically by about 6 meters. In here it moved downwards by 2 or 3 meters. The result is about 1 trillion tons of water displaced. A guy we work with, a guy called Eric Geist from USGS in Menlo Park in California, produced this simulation of what happens then. So we now have a massive bulge. The vertical exaggeration is very significant here, but that's about 6 meters high. And over the next 10 hours or so, that bulge collapses. When the wave hits shallow water, then the wave is forced to become shorter wavelength. With the same amount of energy, that means you must increase the height. And the result is that when the wave hit shallow water on the edge of Sumatra here, the waves went up to 50 meters high. So a 6 meter wave, when it hits shallow water, goes up to 50, 60 meters high. And then it spreads out over the Indian Ocean. 2 hours after the earthquake, there were 30,000 people killed on the coast of India and Sri Lanka. Most of you guys who are doing physics, I could teach you the physics of how this works very easily. This is really school physics, and yet 30,000 people died because we weren't ready to apply that physics to save their lives. I suggest that had they been American or Australian, and indeed the tsunami in Japan last year killed nobody in the far field at all on the other side of the ocean, whereas this killed 30,000 here, and it even 10 hours afterwards, it killed 600 or 700 people in the Horn of Africa. So there is a clear problem where the scientific work that we're doing appears to be being systematically withheld from some people, particularly poor people in the developing world. This is the city of Banda Aceh in northern Sumatra before the tsunami hit, and this is the same area immediately afterwards. 80,000 people were killed almost instantly. And again, 80,000 people, lots of people were going to die. There's no way that an event like this doesn't kill people. But it's the right form of education, the right understanding of the threat probably could have reduced the impact of this, and that's something I'll get back to later in the talk. Okay, so why is somebody from Derry interested in earthquakes that are happening in Sumatra? And we've got our own earthquakes in Lough Swilly. Making a big splash in the newspapers, isn't it? The Donegal Democrat anyway. The first thing I've already mentioned is that the islands along the outer arc in Sumatra allow us to put instruments right on top of where the earthquakes happen. I'm not going to go into these are quite complicated diagrams, but one of the reasons why the earthquake last year in Japan caused such devastation is because there was nowhere you can put instruments. There's no islands on the subduction zone of the east coast of Japan. So I could talk to you a lot about this. There's some really important lessons in geophysics to be learned from these slides. But the most important thing is all the instruments, and these arrows are the movements of GPS instruments immediately following the earthquake. You can see where all the instruments are. They're all on land, and you can't put any out where the earthquakes happen. Sumatra's great for that. The next thing is, I always hated biology. I don't know why. I'm sure it was nothing to do with the biology teacher in St. Columns all those years ago. But the way these corals grow is the most amazing thing. The corals grow from the seafloor in shallow water up as a hemisphere until they hit the surface, and they can't grow above the water, so they stop growing as a hemisphere and instead they start growing as a disc. Now, if the depth of the water was the same always, then that disc would just be flat on the surface. It turns out, of course, because of the seismic cycle, the islands are being pushed downwards, which makes the water deeper as time goes on, and instead we can see that the surface of the corals grow on a slope, and that slope tells us how fast the island is being pushed down, and these corals grow for 1,000 years. So rather than now depending on GPS instruments, which we've only designed in the last 10 years or so,